Hello, Woodstock students. This is Mr. Brennan with some new thoughts about monomers and polymers. Recently, you've been looking at the construction of maltose from two glucose monomers. And today I want to take a look at other variations on that. Okay, but before we jump into that, let's just remind ourselves of what we're talking about here. Monomers are individual building blocks here. I'm showing 5 monomers, just kind of generically as circles. And these, we've been looking at carbohydrates, but these could be monomers of proteins or monomers of lipids and so forth, different categories of like biological molecules. But in general, they're basic building blocks. And then when they get strung together, like shown down here, if 2 of them come together, that might be referred to as a dimer, like D-I-M-E-R. And then 3 might be called a trimer, I suppose. But basically, a long string of them becomes known as a polymer, and that's basically what we've been looking at on the big scale when we talk about, say, grains of salt or grains of sugar. These are long strings of polymers in 3 dimensions. I should say long strings of monomers creating polymers in 3 dimensions of those very familiar kinds of foods. So we're going to take a look at a variation on like what happens when 2 monomers are brought together today. Like I said, we've already looked at the glucose connection that winds up creating something called maltose. We'll look at other variations in a moment. So here's an illustration of 2 monomers. You see on the left is the familiar glucose, and on the right is something that may sound somewhat familiar, but is a molecule we haven't talked about yet called fructose. The interesting thing about these 2 carbohydrates is that they both have the same chemical formula. C6H12O6 is our familiar formula for glucose, and fructose is exactly the same, C6H12O6. But you can see the shapes are different, right? That the glucose is kind of a hexagon ring with an oxygen in one corner and carbons at other corners. And the fructose is just a pentagon where instead of just having one carbon that's off the ring, like you see in glucose here, there's 1 and a second one down here. And the numbering of the carbons is a little bit different. The first carbon here on glucose swings around with like the 6th carbon being off the ring, and that first carbon for fructose is off the ring and connected to another carbon down here, and then the 6th one that goes off. Okay, so 5-sided structure versus 6-sided structure. Okay, and now in the recent past, we've looked at how glucose and glucose can come together to create a double molecule called maltose. But I want to take a look in a moment at how glucose and fructose can come together to create something else. Okay, so notice how the 2 molecules up here are shown independently, and then this arrow shows how they get grouped together. Okay, and then down here it says you've got this sucrose molecule, this double molecule right here, now called sucrose. Okay, and the bonding element between the 2 is an oxygen. And there's a water that's shed out of this combination. And where does that water come from? Well, notice up here that the OH group that hangs down from the first carbon here, and the OH group that hangs down, excuse me, from the second carbon in the fructose, that those 2 OHs can combine to give you H2O plus another O that holds the 2 parts together. So this is familiar to you as dehydration synthesis, right? And it's the same process that brought 2 glucoses together and bring together glucose and fructose. there's no real difference in the bonding idea, right? It's just a different starting point. So instead of two glucoses, it's a glucose and a fructose. When they come together, that combination is known as sucrose. Um, Another thing that we need to note here is that this process can continue because there's an OH hanging down over here and an OH hanging down over here. And if this whole uh, double molecule, if this sucrose were to be replicated, if we had two sucroses, then this OH on this side and that OH on that side could also be combined, releasing a water molecule, leaving behind an oxygen, and that string could be strung out indefinitely. So instead of just creating a double molecule, it could become a quadruple molecule or much longer. It could become a long polymer of sucrose. As long as you have this alternating glucose structure and fructose structure, that would create the familiar polymer string known as sucrose. Now, on the left-hand side here, we see that picture simplified, I suppose, with a glucose and a fructose here, and the OH is coming together to leave behind an O and a water molecule to create that sucrose molecule, okay? So that's the glucose-fructose combination. So it turns out, in summary, that there are three kinds of monomers in the carbohydrate world. These are called monosaccharides, or single sweeteners, if you will. There's glucose, and there's fructose, and then there's a variation on glucose that's known as galactose. Okay, and in every polymer involving the monosaccharides, there has to be at least one glucose in the mix. So there's then three different kinds of sugars we can create from these three monosaccharides. Glucose, when combined with itself, will create maltose. We saw that earlier this week. And glucose, when combined with fructose, will create a molecule known as sucrose. And when glucose is combined with galactose, this is the kind of sugar you might find in milk, that is referred to as lactose, okay? So milk or any other dairy product. So those are three kinds of disaccharides, and of course those can be replicated to create polysaccharides of maltose, sucrose, and lactose, okay? One last thought here. Here we see the combinations of glucose along with other monosaccharides, right? The sucrose, the lactose, the maltose that we just talked about. And notice in each case, right, there's that bonding oxygen left behind from the dehydration synthesis, and that would be found on the right and left-hand sides of each of these in long strings or polymers of these, okay? Now, the reverse process can play out. If we had a long polymer, like of sucrose, right, sugar, that we typically, table sugar, if you will. If we were looking to dissolve that, to break that down, the opposite process can occur by adding water to the mix. Okay, by adding water to here, we can restore the two original OH bonds, or two original OH groups, I should say, on either side of these monomers, and this oxygen bond would be broken. Same thing for lactose, same thing for maltose, that each of these joining points right here can be broken apart by adding in water, which will allow the OH groups to be replenished on each of the individual molecules. So long polymers of sucrose or lactose or maltose can be broken down into their individual components of glucoses and fructoses and galactoses by just adding water, and that will break up all these oxygen bonds here and restore the OH groups to both sides of the individual molecules. Okay, so those are some variations on maltose. Okay, a limited number of variations, but all with the same common theme, right? Of bringing together OH groups from corresponding monomers and releasing a water molecule in a process known as dehydration synthesis. Okay, thanks.